Hello and welcome back. Today we are going to discuss about higher order linear ODEs. So let's start. We already discussed about second order linear ODEs, and this higher order linear ODEs, you'll see that it's natural extension of concepts of 2D. Second order. Okay, so let's start. So we are going to talk about any general order n. So first let's see what is the general form. So the general form is an. This an, I should say this is a function of x, because we are not saying this is constant coefficient, times the nth derivative plus an minus 1x times yn minus 1th derivative, like this, till a1 the first derivative a1x, because this also can be a function of x, first derivative, plus a0 x equal to fx. These ai's and this fx is a function of x. So this is the general form of higher order ODE. Order here is n, and this is non-homogeneous if fx is non-zero, and this is homogeneous if fx is 0. So we write associated homogeneous equation by substituting fx equal to 0. So the associated homogeneous equation will be anx, the nth derivative, an minus 1x, the n minus 1th derivative, so on till a1x first derivative, a0x equal to 0. So we make the associated homogeneous equation by substituting our fx equal to 0. Okay. So if you remember, we studied about principle of superposition when we were talking about second order ODE. So similarly we have principle of superposition here. Which says, for homogeneous equation obviously, it says if you have y1, y2, yn, like it need not be n, say any k, solution of homogeneous equation, then any linear combination, then y, which is linear combination of these solutions, is also a solution to the homogeneous equation. For order 2, we discussed that if you have two solutions, if you take the linear combination, the linear combination is always going to be a solution. If you have more than two solutions also, this thing still holds. If you have any number of solutions for homogeneous equation and you take the linear combination is again going to be a solution. Okay. Let's define linear independence for n functions or for any number of functions, you can say. So f1, f2, fn, any number of functions, these are said to be independent linearly independent. And what's the condition? If we have a zero linear combination, so if we have a linear combination which is equal to 0, c1 f1 plus c2 f2 plus cn fn equal to 0, if we have a linear combination which is equal to 0, then this linear combination must be zero combination. It means all the constants should be equal to 0. Only zero linear combination gives the value 0. Or in other words, we also say any function cannot be written as a linear combination of other functions. And we say functions are linearly dependent, like the set of functions, they are linearly dependent if the set is not linear independent. The set of function is not linearly independent, then we will say okay, this set of functions is linearly dependent. Let's see one example. And the example is, let's talk about these three functions: e power x, x e power x, and e power 2x. We want to check if these functions are linearly dependent or independent. And so what we'll do is, we will take a journal linear combination c1 e power x plus c2 x times e power x plus c3 e power 2x equal to 0. If somehow we can prove that c1, c2 and c3 are equal to 0, then these functions are linearly independent. If we can prove at least one of them is non-zero, then the set is linearly independent. Okay, let's try to check the values of c1, c2 and c3. Can you please turn on the AC? Okay, so let's find out the value of c1, c2 and c3. So if you substitute x equal to 0, which is the simplest value to substitute always, you will get c1 e power 0 is 1, second term is 0, e power 0 is again 1. So if we substitute x equal to 0, we get c1 plus c3 equal to 0. If we substitute x equal to 1, we will get c1 e plus c2e plus c3 e square equal to 0, right? If we substitute x equal to -1, we will get c1 e power -1 plus, we have x multiplied, so minus c2 e power -1 plus c3 e power -2 equal to 0. Okay. Let's mark these equations so you don't get confused. So from first equation, we get C3 is equal to negative C1, right? From 2, like 2 can be rewritten as, okay, let's keep it as it is. So I am writing 2 again over here as it is, C1e plus C2e, but substituting C3 as negative C1. This is our equation 2, and we are multiplying equation 3 by e power 2, e square, and we will get, if base are same, we add the exponent. So 2 minus 1 is 1, so we will get C1e minus C2e minus, oh, oops, I forgot e here. This is e negative 2. So C1 equal to 0. This is what we will get. Okay. If we add these two equations, the last two equations, if we add them, C2e will cancel out, and what we will get is C1 2e minus e square minus 1 equal to 0. This is what we will get. Okay, and then this is a constant number, and you can check this is not equal to 0. This, if you see it carefully, this is basically C1 e minus 1 negative of e minus 1 square equal to 0. E is not equal to 1, so this over here is not equal to 0, and this implies C1 is equal to 0. If C1 is equal to 0, C3 is negative C1, C3 is equal to 0. Okay. If you substitute the value of C1 and C3 in equation 2, you will get C2 equal to 0. So this implies that e power x, x times e power x, e power 2x are linearly independent. In fact, e power r, e power r1x and e power r2x are always linearly independent when r1 is not equal to r2. If you multiply with x power n, it's also going to be linearly independent than e power r1x. Okay, so this is how we in general check linear independence. We substitute the general sum equal to 0, and then we prove that the coefficients are equal to 0. Okay. Next we are going to define the Wronskian. We defined the Wronskian of two functions previously. This time we are going to define the Wronskian of n functions. So Wronskian of, say, f1, f2 up to so on fn is defined as the determinant. So in the first row you keep them as it is, f1, f2 up to so on fn. In the second row you are going to take the first derivative. So f1 first derivative, f2 prime, fn prime. In the second row you will take the second derivative. In the third row you are going to take the third derivative, and in the last row we are going to take the n minus 1th derivative. So basically there are total n rows. This is n cross n. So there are total n rows. In first row we are keeping the function as it is. So in the last row we are reaching till n minus 1th derivative. Okay. Let's calculate the determinant of e power x, x times e power x and e power 2x. Wronskian of e power x, x times e power x and e power 2x. So this is going to be, in the first row we keep them as it is. E power x, e power 2x. In the second row we take the first derivative, x plus 1 times e power x, e power 2x, or basically in this step we are using the product rule. We keep the first function as it is, take the derivative of second one, plus we keep the second one as it is, derivative of x is 1. And then we take the second derivative, plus e power x, and derivative of e power x is e power x again, 4 times e power 2x. So what we got is e power x, x times e power x, e power 2x. So first column is e power x, second column here we have x plus 1 e power x, x plus 2 e power x, 2 times e power 2x, 4 times e power 2x. Okay, so this is the determinant we want to find out. If you remember some properties of determinant, so either you can directly calculate this determinant or you can use some properties. So the property I am going to use is, you can pull out any term from the column or from the row if it's common. From the first column we can pull out e power x, from the second column we can pull out e power x, from the third column we can pull out e power 2x, and what we are left with is 1 1 1 x, x plus 1, x plus 2, 1 2 4. Okay, let's find out the determinant now. So we have e power 4x outside, I hope you know how to calculate the determinant. So it's 1 times, so we choose the first row, first column entry, times, we don't select any of the column and row entry, times 2 x plus 2 4, first row second entry multiplied with 1 2 1 4. This determinant, basically we are not choosing this row and this column then, and then we are going to plus 1. Now we are not going to choose our first row and third column, so 1 x plus 1 1 x plus 2. So what you'll get is e power 4x 4x minus, okay, so basically evaluate this, and what you will get is this is equal to 1. So your determinant is equal to e power 4x, which is not equal to 0. So remember, in case of order 2, we had a result about Wronskian and linear independence, that the Wronskian is non-zero if the functions are linearly independent. Similarly, these three functions are linearly independent and the Wronskian is non-zero. These three functions are linearly independent and the Wronskian is non-zero. Actually, this is no coincidence. We have the similar result in n order also. Let's give it the same name, independence and Wronskian. Independence and Wronskian. And what it says is, suppose you have y1, y2 up to so on, yn, n solutions of homogeneous nth order equation, then what will happen is y1, y2, this set up to yn is linearly independent if and only if Wronskian is non-zero at each point. Okay, and the second case is if they are linearly dependent, this set is linearly dependent. This can happen if the Wronskian is identically equal to 0. So you have only two cases. Either the Wronskian is going to be 0 on all the points, or it's going to be non-zero. If it's non-zero, the functions are linearly independent. If it's 0, the functions are linearly dependent. So in the previous case, the Wronskian was non-zero, so we can conclude from here also that x, e to the power x, e to the power x and e power 4x are linearly independent. So we are going to stop here in this lecture, and in the next lecture we are going to talk more about higher order homogeneous equations. Till then, bye bye, take care and practice more and more problems.